So we're going to go into an extended example, and it's going to be about what's called a mass spectrometer. So the way that people do radiocarbon dating is that what they look for in a sample is they look for two isotopes. And one of those isotopes decays predictably. And so for example, in like a pre-calculus class or an algebra class, you talk about how there's an exponential decay of the radioisotope. And so we look at the beginning, we had like 100% of something, and then it would predictably decay following the exponential curve. And then we would be able to use that to figure out, well, if we have 50% left of the isotope, based on what we assume was the 100% early on, then we could tell basically how old something is. So here is how we actually would separate those isotopes. So we have two of these carbon isotopes, and what we do is we send them through basically a magnetic field. We send them through, and then we look at the radius of their loop, their half circle. So we send it through the magnetic field, and then it hits kind of like a receptor here to see where did it land. And depending on how far away it lands from where you send it in, you can basically tell what the mass is. And because they have different masses, you would be able to tell which one's which and measure it. So here is the example we're going to use, and we're going to use the carbon 12 and carbon 14. So we're going to assume in our example that the velocity is going to be 1 times 10 to the 5th meters per second. And I'm taking this from the book. This is a really good example. The magnetic field here is going to be about 0.1 teslas. And we want to basically tell, if we have carbon 12 and carbon 14, what are the radiuses, the radii of both of those circular paths. Okay, so we have to do a little work here first, because what we need to do is for carbon 12, we want to know what the mass of that is. Okay, and so what this means here is that we have 6 protons, we have 6 neutrons, and we have 5 electrons. So normally there are the same protons and neutrons, and because there's a plus here, we have one less electron, meaning that it's a positively charged ion. Similarly for carbon 14, well, the 14 tells us that yes, we have 6 protons, but we're going to have 8 neutrons, which will make it a little unstable and decay, and then we'll have 6 electrons. Okay, so if you're ever to do an example like this, you would be given, or you'd be able to look up the mass of each of these pieces. So a proton is worth 1.67 times 10 to the negative 27 kilograms. A neutron is the exact same thing, but an electron we know is 9.11 times 10 to the negative 31. And so before we get started here and actually use the radius equation from magnetism, we need to figure out if we have 6 protons, 6 neutrons, and 5 electrons, how much will that be total? So basically you're going to do 6 times that, plus 6 times that, plus 5 times the mass of an electron. Okay, so I paused actually and calculated this, and then I wrote down the mass of a carbon 12 is 2 times 10 to the negative 26 kilogram. So we're going to do the same thing here. We'll do 6 times the mass of a proton, 8 times the mass of basically a proton because they weigh the same, and then 6 times the mass of an electron. And when we do that, we're going to get a mass of 2.3 times 10 to the negative 26 kilograms. By the way, the mass of an electron is so small that it's actually not the electrons at all that are really changing the mass. What really is changing the mass is the extra 2 neutrons here. Okay, so here's what we need to do. We need to find the radius. If we launch one of these carbon 12s into this magnetic field, we just want to know what the radius of that circle will be. And back in our notes, we have that we're going to use mass times velocity times the charge all over the charge times the field. Okay, so the mass we found is 2 times 10 to the negative 26th. The mass is going to be 1 times 10 to the 5th. I want to make sure I wrote that down. Yep, 1 times 10 to the 5th. Now the positive on the ion here means that there is one less electron than protons, and so the net charge is going to be 1 positive, but we're still going to be using 1.6 times 10 to the negative 19th coulombs, and then the magnetic field here, they gave us a strength of 0.1. Let's crunch that. When I work all that out, I get 0.13-ish, 0.125, but 0.13 meters. Okay, now if you work out the same thing on the other side, the radius of a carbon-14, this was the radius of carbon-12, we would do the same calculation, we would just be switching the mass. And so, working all these numbers out, I got 0.14 meters. And so, if you were to run this experiment and be doing this to separate out the isotopes, you would have a difference of about 0.01 meters, or that's about the same as 10 centimeters. So you'd be able to collect 14 in one area and 13 in another. You'd be able to separate them out and tell them pretty clearly apart.